present my recent work at KAIST, where I obtained my PhD. So first of all, I'd like to thank Professor Dong-Soo Kim and Professor Sang-il for this opportunity. In this talk, I'm going to give a interesting thing on non-crossing partitions. Okay, so here's the outline of my talk. So non-crossing partition, the set of non-crossing partition was first studied by Creras almost in 40 years ago, and after that, it has received a lot of interest, both in combinatorially and algebraically. And quite recently, Basis, Brady, and Watt defined non-crossing partitions for each finite reflection group W, such that non-crossing partitions of type A is isomorphic to the original non-crossing partition. And for classical types, say type A, B, C, D, we have combinatorial models. For type B, which is isomorphic to the non-crossing partition of type C, has a combinatorial model defined by Wig-Reiner. And for type D, we also have a combinatorial model. So the main purpose of this talk is to find interpretations for non-crossing partitions of type B. So type D non-crossing partition is a special case of type B non-crossing partition. So all of our method can be applied to type D non-crossing partition. So it's type B, D is enough to consider for all classical reflection groups. So let me define non-crossing partitions. So bracket n means the set of integers from 1 to n. It's a usual notation in combinatorics. And a partition of n is a collection of subsets satisfying these conditions. This joint union is the whole set n, and they are all non-empty, and they don't intersect each other. And each element in a partition is called a block. Capital pi of n is the set of partitions of n. So for example, this is an example. So this is a partition of 7. And the standard representation is a very natural way of representing a partition in this way. If we have a block, we connect all the integers in the block by an arc if they are adjacent. So 1, 4, 6, because we have a block containing 1, 4, 6, we connect 1 and 4 and 4 and 6. This is a very natural way to represent a partition. So before defining non-crossing partition, let me ask you a simple question. Do you think this is a non-crossing partition or not? Maybe even though I didn't define the non-crossing partition, maybe you will guess that it's not. So non-crossing partition is just a partition without crossing in this standard representation. So this is not a non-crossing partition, but this is a non-crossing partition. So this is the main object of my talk. So, NC of n is the set of non-crossing partitions of n. So the first question that one may ask for non-crossing partition will be the Catalan, the cardinality. So it is well known that the cardinality of the non-crossing partition is the Catalan number. So I think Catalan number is the most well-known number sequence or number in combinatorics. Richard Stanley, who is a professor at MIT, has collected 176 combinatorial objects which are counted by the Catalan number. So non-crossing partitions is one of them. I think the most well-known Catalan object is the path. So there's a very simple bijection between non-crossing partition and Dick path. So by a Dick path, I mean a lattice path from the origin to n, n such that it never goes below the line y equals x. And the bijection goes in this way. For each integer from 1 to n, I will construct 2 consecutive steps in the lattice path. Here, if 1 has an arc only to the right, then we make 2 up steps. So we have only 1 arc to the right, so we construct 2 up steps, 1 and 2. Okay? And 2 is the same. It has only 1 arc to the right, so we draw 2 up steps like this. So we have 4 configurations for each vertex like this. It may have 1 arc to the right like this, or this, or nothing. So in this case, we draw 2 up steps. In this case, we draw 2 east steps. And here, we draw 1 east step followed by an up step, and up steps and east step. So 3 here correspond to this configuration. So we draw 2 consecutive east steps. And for this integer 4, we draw east step and an up step, and so on. And this is, in fact, a bijection. You can easily check that what we get is, in fact, a dig path. So dig path, usually in this discrete math course, you will learn the number of dig paths is the Catalan number. So we have proved that cardinality of NCN is the Catalan number. During the talk, I will find another proof of this fact. Okay? Any questions so far? So we have seen the number of the cardinality of the non-crossing partitions, but we have a couple of refined result, which is this. For non-crossing partition, the block size vector is defined by this sequence, such that B is the number of blocks of pi, and I wrote B semicolon and B1 up to Bn. So Bi is the number of blocks of size I. So of course, B is the sum of Bi's. So, for example, the block size vector of this non-crossing partition is given by this sequence. We have 4 blocks of size 4 blocks, so the first number is 4, and we have 2 blocks of size 1, so the first one is 2, and we have 1 block of size 2, and 0 block of size 3, and 1 block of size 4. So the block size vector is this. And KAIST proved this refined result. The number of non-crossing partitions with the fixed block size vector is equal to this nice number. Okay. And we can consider non-crossing partition, the set of non-crossing partition, as a post set, partially ordered set. And the order is defined this way. Pi 1 is less than or equal to pi 2 if and only if pi 1 is a refinement of pi 2. It means that pi 1 is more partitioned than pi 2 in this sense. Each block of pi 2 is a union of several blocks of pi 1. So this is the set diagram of NC of 3. As you can see, each block of this partition is a union of several blocks of this. This block is a union of this block, and this is a union of this block. And you can see that this poset is graded with the this rank vector, rank function. So this is rank 0, rank 1, and rank 2. And the rank can be calculated in this way, n minus the number of blocks of pi. So n here 3 minus the block 3 is 0. So 0, 1, 2, and so on. So if you know the number of blocks, then you can compute the rank. And a multi-chain is just a chain with possible repetitions. So I allowed equality here. So a multi-chain has rank jump vector S1 up to SL plus 1 if I added the minimum element here and the maximum element here. So here, in this non-crossing partition poset, we always have the minimum and the maximum, so we can do this. So, and then we compute all the ranks of them, and we compute the rank difference. That is the rank jump vector. So, if we have L element, then the rank jump vector consists of L plus 1 integers. And the sum of the integers in this vector is the height of the poset, which is n minus 1. Okay? And because of this relation, the number of blocks is decreased by S1 and S2 and so on. Okay? So here is the result of Edelman. The number of multi-chains with given rank jump vector is equal to this, which is very nice formula. And I will show you a couple of consequences of this theorem.
The sum of SI should be n.
N minus 1.
Oh, okay, n minus
1. Yeah, because the maximum has 1 block, so the rank is n minus 1. So let's see. If a partition has k blocks, then that partition can be considered as a chain consisting of itself. So a partition with k blocks is equal to a multi-chain with rank jump vector n minus k, comma k minus 1. So if we plug in these two numbers here, then we get the number of partitions with k blocks is equal to this number, which is called Narayana number, which is also a well-known number in combinatorics. And we can compute the number of maximal chains. By a maximal chain, I mean a chain which we cannot add any element to it. It's a chain which is maximal. It's a maximal chain. So in other way of defining maximal chain is that it is a chain with this rank jump vector. The rank jump vector is increased by only 1 with n minus 1 once, because the sum should be the height, which is n minus 1. So if we plug in these numbers here, then we get this. The number of maximal chains is n to the n minus 2, which is also a well-known number, which also counts the number of labeled trees with n vertices, or it is proved that the number of maximal labeled trees with n vertices is equal to this by so-called prefer code. And it also counts so-called parking functions, and Richard Stanley found a bijection between this object and the set of parking functions. And it is also closely related to the minimal factorization problem of a permutation. Okay. So we have seen two results on non-crossing partitions, and very recently there is a theorem by Kratanteller and Müller which generalize both of the two previous results. The number of multi-chains in the non-crossing partitions for set such that the rank jump vector is fixed and the block size vector of the first element is fixed. So it generalizes both of the previous results. And rather surprisingly, it also has a very simple, nice formula. Is equal to this number. And in the same paper, they proved analogous formula for non-crossing partitions of type B and type D. And none of them are combinatorial. So they proved that quite complicated method which I cannot understand. So they, in combinatorics, if we see this kind of nice result, combinatorial result, and then many combinatorialists want combinatorial proof rather than some complicated calculation. So they also asked in the introduction that the theorem for type AB seemed amenable to combinatorial proofs. However, to find a combinatorial proof of the theorem for type D seems rather hopeless.
Is this type A or something?
Type A. For type B and type D, we have similar formula, which I didn't write here. I will define them later. Yeah. So, yeah. But I proved all of them combinatorially, actually. But I'm not going to prove them combinatorially in this talk, but I will present my the most important ingredient of my proof for them, which is a new interpretation for non-crossing partitions of type B. Here, as you see, they wrote that type D is difficult. They thought type D is difficult, but I only interpret type B non-crossing partitions, but it works for type D because type D non-crossing partition is a special case of type B. So I will only speak of type B non-crossing partition in my talk. So, yeah. So main purpose is this is my motivation for this talk. So give a new interpretation for type B non-crossing partition, which allows us to understand type B non-crossing partitions as easily as type A non-crossing partition. I will relate type B with type A, which is the original one and the easier one. And yeah. Okay. So here's a definition of non-crossing partitions of for finite Coxster group. So actually, this is a definition. Definition goes like this, but yeah, we don't need this algebraic definition because we have combinatorial model for them, which is easier to understand than this, at least for me. So instead of spending more time on this, I will just show you this slide, and I just want you to forget this. Okay. So this is an algebraic definition, but I will define type B non-crossing partitions combinatorially. Okay. To do that, we need to define type B partitions first. So a partition can be considered as an intersection of reflecting hyperplanes of the Coxster group of type A, which is this. So this is a set of hyperplanes. Okay. For example, this is a partition, and we can identify this partition as an intersection of hyperplanes like this. So this is an intersection of the hyperplanes x1 minus x4 equals 0, and x4 minus x6 equals 0, and x2 minus x3 equals 0, x3 minus x7 equals 0. So they are, it's very easy to see that they can be identified. So type B partitions is clear to define type B partitions, which is just an intersection of reflecting hyperplanes of type B, which is the set of these hyperplanes. So here we may have xi equals xj or xi equals minus xj or xi equals 0. So this is an example. So this is an intersection of type B hyperplanes, and we can identify this with this partition. So 1, minus 3, and 6, and negative copy of them. 1, minus 6, 1, minus 3, 6, and minus negative copy of this is minus 1, 3, and minus 6, which I will just simply write as plus minus of this. Okay. So, and if we have some coordinates equal to 0, then they correspond to this kind of block, where I and minus I are in that block. So this is a definition, but let me give you a more precise definition of type B partitions. So a partition of type Bn is a partition of plus bracket of plus minus n, which is the set of integers from 1 to n and minus 1 to minus n, such that if B is a block of pi, then minus B is also a block of pi. And there is at most one block called 0 block, which satisfies this relation, B equals minus B. So in this example, we have a 0 block, 2, 4, minus 2, minus 4. So the negative copy of this is itself. And the condition 2 is obvious from this. If we obtained a partition by this intersection, then we always have these two conditions. Any questions? So capital pi sub B of n denotes the set of partitions of type Bn.
So is it obvious to see that those two are equivalent?
Sorry?
I'm wondering whether it's obvious to see the partial definition implies double or
No.
no?
There's no relation between these two.
No. To see the above definition, the section of the...
Yeah, it's quite obvious, in fact. Because of the construction, the first one, you may think the first one is obvious. I think the second one is less obvious than the first one. But it is also quite obvious because if 0 block always come from this kind of thing. So if we have another 0 block, then it is also equals to 0, so they must be the same. We cannot have other things, like x, if we have x9 equals 0, then it also equals to this. So they must be in the same block. That's why we have at most one 0 block. Yes. Okay. So I found the formula for the number of partitions of type B, which is the sum of this. This is the Stirling number of the second kind, and Tn is the number of involutions of n. And one can compare this with this rather obvious formula. The number of partition is the sum of the Stirling number of the second kind. Actually, the Stirling number of the second kind, S n, k, means that the number of, it simply means that it is the number of partitions of n with k blocks. So this is obvious. We have some kind of type B analog formula for this. It's not obvious, but yeah, because I will not use this fact, so I will not prove this. I just want. Yeah. So here's the combinatorial model for type B partitions. A non-crossing partition of type B is a partition of type B without crossing in the standard representation with this order. So we arrange integers in this way, in this order, and we represent it as a standard representation, like a standard representation. And if we don't have any crossing, then it is a non-crossing partition of type B. Okay? Because of this condition, we have that 1, 4, minus 5 are in the same block, so the negative copy is minus 4, 5, minus 1, and minus 4 are in the same block. And in this case, we don't have any zero block, so it's a type B partition. So NC B of n is a set of non-crossing partitions of type B, and it has been proved that it is isomorphic to the algebraic definition of non-crossing partition. So we can forget about algebraic definition, and we can only focus on this combinatorial model. In fact, we could have defined the non-crossing partition in this way. Maybe it's the shortest way to define non-crossing partitions of type B. The circular representation is just a representation by a circle and convex holes. If we draw a convex hole if the integers are in the same block. So this is the same, it represents the same partition as this. And the non-crossing part, it is a non-crossing partition if and only if it is the convex holes are non-crossing and it is invariant under the rotation. And you can also see that the zero block, if it exists, corresponds to the block containing the origin. So we don't have a zero block here, and we have a zero block, which contains this. So the zero block, there is at most one zero block is kind of immediate. But my interpretation is based on this representation, so I will focus on this representation. Okay? So let me define a very simple map from a non-crossing partition of type B to some kind of object related to type A non-crossing partition. I think, as you see, it's a very simple map, so nobody cannot understand. Okay? I think this is the simplest map that one can imagine. Map is just this. Just delete the negative part. This is my map. So at the first time that you see this map, you may think that we have lost several informations. But in fact, we didn't lose any information from this. We can reconstruct this only from this. So let's see this object. This is a non-crossing partition of type A, the original non-crossing partition, with several edges sticking out from some blocks. So this is the object that we obtained by doing the map. So let me reconstruct the original type B non-crossing partitions. The first way to do that is this, just arrange negative integers. And because it is a type B partition, if we have a block here, 1, 4, 5 are in the same block, so the negative copy must be in the same block. So 1, minus 4, minus 5 must be in the same block. So we can draw in this way. And the block containing 1, 4, 5 has at least one negative integer. So the negative copy of that block, we must have at least one positive integer in this block. So we must have this kind of edges. And we have to connect them. But there is only one way of connecting them. This one cannot be connected to this, because otherwise it causes a crossing. So there's only one way to connect this, which is this, and this to this, this. So we have reconstructed that. So in fact, this simple map is invertible. So this map is invertible. So it's a bijection from this set to the image. So it's time to see what the image can be. So you can think that this is kind of a pair of non-crossing partition of type A with several blocks of them, blocks of the partition. So let me define this notion. A block is called nested if there is an edge above it. So this block is nested because it's nested by this edge. So it's a very intuitive definition. This block is not nested, but this block, this block, this block are nested. This block is not nested. Okay? Otherwise, it's called non-nested. So NC super NN of N is the set of pairs sigma comma X, where sigma is a non-crossing partition of type A, and X is a set of non-nested blocks of sigma. And in fact, this is the image of this map. You can easily see that the blocks having an edge, red edge, is nested, non-nested. Because otherwise, if this is nested, then we cannot connect this to a negative integer. So the chosen blocks in X must be non-nested. And in fact, if we have this, then we can construct reconstruct the first one. So this is in fact the image. So this is my first interpretation for non-crossing partitions of type B. So it's just a non-crossing partition with several blocks chosen. And so this is a bijection. So I have another interpretation. Script B of N is the set of pairs sigma comma Y such that sigma is a non-crossing partition as before, and Y has three choices. It can be either the empty set, and it can be an edge of sigma. By an edge of a partition, I mean the arc in the standard representation. So I didn't define the edge yet, but if we have this partition, something like this, then these are edges. Okay? Or a block of sigma. Okay? That's all. And you can see that it is in fact equal to the Cartesian product of this and this. Because for given sigma, non-crossing partition sigma, we have n plus 1 choices for y. So first one, there's only one choice for first one. And if we have k blocks, then we must have n minus k edges. So we have 1 to 3 blocks, and we must have n minus 3, 2 edges like this. So for the choices for 2 and 3 is n. So we have n plus 1 choices in total. So you may consider this as this product. Okay. So for this pair in this set, X is a non-crossing partition, and sigma is a non-crossing partition, and X is a set of non-nested blocks of sigma. And I will define an element in this set as follows. So this is an element in this set. So sigma is this, and X is empty. We don't have any red edges here. So X is empty. There is no chosen block. Then sigma is the same, and I think I should put sigma, no, sorry. And Y is the empty set. And we have, if we have several chosen blocks, so these 4 blocks are the blocks in X. Then we just connect them in this way. We just connect the first one to the last one. and the second one to the second last one, and so on. So in this case, we have even number of chosen blocks, even number of blocks in X. Then we can connect all of them in this way. And then this is the partition, and Y is the edge. Is the edge that is the innermost edge which has been added. So we have two added edges, and this one is the innermost one. So edge Y will be this edge. So it is this red edge. We also can have even number of chosen blocks. By chosen blocks, I mean the blocks in X. Then we just do the same thing, but we cannot connect all of them because we have odd blocks. So at the end, we have only one block. In this case, we let Y be this block. So in this case, Y is empty edge block. Okay? And this is also invertible because empty then is obvious. We have an edge, Y is an edge, then we delete Y and all the edges that nested. We just cut these two, and we can construct this. And if Y is a block, then we delete all the edges of our bit, and the divided blocks are the chosen blocks together with this block Y. So this is in fact also a bijection. So script B is my second interpretation for non-crossing partitions of type B. So using this interpretation, I proved Cartan-Taylor and Muller's theorem for type D. So this interpretation was the important argument. So as an application, we can prove interesting theorems of type B non-crossing partitions just using that interpretation. So this is the result of Creveras that I have shown to you at the beginning. And there is a similar result for type B, which has been proved by Athanasiadis in 20 years ago, 12 years ago. The number of non-crossing partitions of type B with block size vector is equal to this, but using my second interpretation, it is almost immediate, almost just 3 lines proof can be proved this. So, and we can relate non-crossing partitions of type B with lattice path. So LP of n is the set of lattice path from 0, 0 to n, n. So the cardinality is 2n choose n. And so this is my first interpretation for non-crossing partitions, which is a pair of non-crossing partition of type A with several blocks are chosen. All right. Then, because this is a non-crossing partition, we have a bijection between them with dict path. So this is the dict path corresponding to this non-crossing partition. And we have several chosen blocks, and they are all non-nested. So if this is a chosen block, then this partition corresponds to a sub-dict path, which is this dict path. And this block corresponds to this dict path. They all start at this line and end at this line. So it is a dict path. And this corresponds to this dict path. So if that block has been chosen, then we just reflect the corresponding dict path across the line. So we obtain this lattice path from 0 to n. And in this way, we can obtain any lattice path. So this is a bijection. So this is in fact a bijection between type B non-crossing partition and lattice path. So the cardinality of type B non-crossing partition is 2n choose n. Actually, that has been known for a long time, but I have proved that in this way. So actually, even though I mentioned that the number of Dick path is the Catalan number, I didn't prove that. But in fact, using this, it is an obvious from my result. So they are all related with the bijections. So non-crossing partition of type B, my first interpretation, second interpretation, lattice path. The cardinality of this is 2n choose n. So they are all 2n choose n. They are cardinalities. So see here, it is this times n plus 1. So the cardinality of this is 1 over n plus 1 times 2n choose n. That's the proof of the number of Dick path is the Catalan number. All right. And with this, we can prove a conjecture by Armstrong, which is this. A partition is called K divisible if each block of pi is of size divisible by K. So all the block sizes are divisible by K. So one divisible is nothing. It's just nothing. And NC K of n is a poset of K divisible non-crossing partitions of Kn. And the cardinality of this is called first Catalan number, which is a generalization of Catalan number, which is also very simple. 1 over Kn plus 1 times K plus 1 times n, choose n. If K equals 1, then it's the Catalan number. Okay? Yes. And Armstrong considered this poset. NC tilde K of n is the subposet of the K divisible non-crossing partition, whose elements are fixed under the 180-degree rotation in circular representation. So if n is even, that is just type B non-crossing partition, as I mentioned, using circular representation. So let me see. So this is an element of this set. All the blocks are divisible by 4, and it is invariant under the rotation. So if both K and N are odd, then there's no partition which is invariant under the rotation because we have odd number of elements. If we rotate them, then even we cannot get, even the vertices are not invariant. So we must have at least one of them even. So the interesting case is this. K is even and N is odd, which is not equal to any known combinatorial object. So Armstrong considered this kind of poset, and he conjectured this. The zeta polynomial, which is the number of multi-chains of length n, is equal to this number. So, in my second interpretation for non-crossing partitions of type B, I could prove this. So, because K divisible means that each block, the size of each block is divisible by K, it must be a partition of n where n is divisible by K, because otherwise it cannot be K divisible. So I extended that definition in this way. R is between -1 and K minus 1, and a partition in this set, K n plus R, is augmented K divisible if all the blocks are divisible by K, but it's not possible. So all but one block of pi have size divisible by K. So it's as K divisible as possible. Except one block, all the blocks are K divisible. And I define this poset, I consider this poset It is augmented k-divisible non-crossing partitions per set. Is k-divisible augmented k-divisible, and I proved that Armstrong's poset is in fact isomorphic to this augmented k-divisible non-crossing partition. And because this is just a non-crossing partition of type A, the original one, so we can compute theta polynomial easily. So I proved this result, and I proved that Armstrong's conjecture is true. And I only introduced non-crossing partitions, but there is a similar partitions called non-nesting partitions. So non-crossing partition do not allow this kind of configuration in the standard representation, but non-nesting partitions do not allow this configuration, just similar. So this is an example of non-nesting partition. And it's also well known that they have the same cardinality. So it's also counted by the Catalan number. There's in fact a simple bijection between non-crossing partitions and non-nesting partitions. And Postnikov defined non-nesting partitions for each classical reflection group, type A, B, C, D, but not for all Coxster group like non-crossing partitions. But anyway, we also have combinatorial models for them, and my method can be applied to non-nesting partitions. So we can interpret type B non-nesting partition in this way. In this case, for type non-crossing partitions, I used non-nested blocks, but for non-nesting partitions, we should use non-aligned blocks. Here, a partition is aligned means it has an arc to the right of it. So this block is aligned because it has a block, it has an edge to the right of the maximal element of it. So this block is aligned. This block is not aligned because we don't have any edge here. So this is the only aligned block here. We focus on the maximum element of the block, so even though we have this edge, but it's not to the right of this. So it's otherwise it's non-aligned blocks. So I define this set, and then NA of n is a set of pairs sigma comma x. X is the non-nesting partition, sigma, and X is a set of non-aligned blocks of sigma. And it's also bijection. My method, deleting the negative integers, also gives us this thing. So for type B, non-crossing or non-nesting partition, we also have a bijection. So I want to relate non-crossing partitions of type B and non-nesting partitions of type B with my interpretation. So this is my interpretation. This is interpretation for type non-nesting partition. So let's see. There is a well-known bijection between non-nesting partitions and non-crossing partition. I just use that bijection. And in fact, that can be generalized to my this set. So we need to relate, to connect them with a bijection, we need to find the bijection between this and this. And so it just means that we need to change non-nested blocks to non-aligned blocks in the set of non-crossing partitions. And I found an involution in the set of non-crossing partitions, exchanging non-nested blocks and non-aligned blocks, which gives us a bijection between them. So that, as a corollary, we have this somewhat interesting result. The number of non-crossing partitions with exactly I non-nested blocks and j non-aligned blocks is equal to the number of non-crossing partitions with exactly j non-nested blocks and I non-aligned blocks. This is a somewhat unexpected result. So with this, I could connect all of them with bijections. And in fact, this preserves the block size vector. So it preserves the block sizes. And in fact, there is a bijection preserving block sizes. Very recent result by Fink and Girardo. And my bijection is different from their bijection. So, yeah. So this is the final remarks. So we have found two interpretations for non-crossing partitions of type B. And as I have shown to you, many interesting properties of non-crossing partitions, I think, can be translated to type B non-crossing partitions using our interpretations. That's all. Thank you very much.